Hello friends, today we are going to talk about one of the most interesting, important part of mechanical engineering, that is bolted joints. Uh, in my opinion, it is mostly underrated topic part from designers' point of view in from many engineers. But whatever failures I have seen since a long time, mostly they come through improper design of bolt selection, improper bolting design, and lack of awareness about the bolting systems. So here I'm going to talk about today a very crisp manner. Why the question to be answered here is, if I'm going to bolt two parts together, how I'm going to make sure that the joint remains intact for a given loading condition. So here it's a simple example shown, like we have two plates which are bolted by a single bolt here. So what mechanically what happens is, you have a external load acting on the joint, that is called as P, and this particular additional load will try to separate out the joint. But what holds the joint together is the preload that is applied. Preload means the actual load, clamping load that is generated due to the torquing given to the bolt, to the torque, contributed to the torque. So what happens is, once you clamp this particular bolt, the effect of the clamping is spread over 3 times diameter of the shank, the diameter of the hole. That is a basic fundamental mechanical systems understanding. It is proven by many FEA analysis also. So the effect of the bolt is surrounded in an area of 3 times diameter. So that is particularly, so if I show this 3 times diameter zone, so this is the particular zone where the effect of clamping will be seen. So technically speaking, this much area will only contribute to the stiffness of the joint, stiffness of the stack up that we are using. Secondly, we have some stiffness of the bolt also. So once you start torquing the nut here, the bolt will have experience a tensile load. So that tensile load divided by the cross section, so the deflection of the bolt divided by the load will give you the stiffness of the bolt. So now here we know the stiffness of the bolt, say KB, and the stiffness of the bolt, suppose say KB, and stiffness of this particular stack up is called as KC. Now, point to note here is, what is a constant parameter, common parameter between the bolt and the stack up. So the common parameter is the preload, because the preload generated on the bolt, the same preload is then reacting in opposite direction on the stack up. So the clamping force on the stack up is actually the tensile force on the bolt. So in this case, the preload is common between. So the preload generated in the clamping system, the joint, is called as, say, PI, and this PI is when I take the case of the joint, so the deflection of the stack up, delta C into stiffness of the stack up KC. So the preload will be equal to KC into delta C. The same thing is true for the bolt. So in case of bolt, deflection of the bolt is preload divided by KB. So now we know that deflection of the stack up is delta C, deflection of the bolt is delta B. So in both the cases, the common parameter is PI. Now let's see what is happening on the bolt side and what is happening on the stack up side. So if I consider the bolt, so once you start applying the tensile load on the bolt is going to elongate. So I have just plotted load and deflection of the bolt in this particular graph. So we start from 0. At 0 load, there is 0 deflection. You go on increasing the load, and the deflection is also increasing. So the relation is linear because of the Young's modulus, the relation is linear. So I go on increasing the preload load till the value of the preload. So Pi is my preload, right? So till this point, the deflection that is occurring on the bolt is delta B. Okay. Similar case will happen in case of the stack up, but understand that in case of bolt, the bolt is elongating, so that is why the deflection is positive. But in case of stack up, the stack up is compressing, so the deflection is in negative direction. That is why I have shown a negative quadrant, or you can say the fourth quadrant of the graph, wherein the deflection is positive and the load is negative. So in this case, what you can see is when you go on increasing the load, the deflection also increases. Now intentionally I have shown a different slope for these two parts because not necessarily you will have same stiffness for the stack up and bolt, stack up and the bolt. So that is why I have seen, you can see the bolt stiffness is different and the stack up stiffness is different. That is why the slope of the graphs are different. So now the stack up stiffness, I have intentionally considered some kind of higher stiffness. So that is why it is showing a stiff graph here. So the stack up is also experiencing the same preload Pi, and so because of the preload Pi, the stack up is compressed by a deflection delta C. So this is the point over here on this slope load and deflection graph of the stack up. Now what I do is I know this Pi is same in this graph and this graph because the stack up is same, the mating parts are same. So the same preload is acting on bolt as well as the stack up. So I know the vertical height of this O to this particular point and O to this particular point is same. So I just shift this line from this graph over here. So I start from here, this point, and I draw the same, I transfer the same line from this graph to this graph. So what actually I have done is I have clubbed the load deflection graph of the bolt and the load deflection graph of the stack up. So what you can see here, the deflection of the stack up for preload is delta C. So the delta C will come over here and now delta B comes over here. So from when I go on increasing the load from this point to this point, 0 to Pi, the bolt is compressed by deflection, bolt has elongated by deflection delta B, and we are going from this point to this point, whereas in case of stack up, the stack up is compressed by amount of delta C by the virtue of load of Pi. So now I go on further increasing the load on the stack up. What happens is the tensile load will go on increasing further. With this load, what you can see here, this particular tensile load is against the clamping that is happening on the stack up. So that is why we are going further over here. We have reached to a load till the preload, and now you have clamped the bolt. Now this particular joint goes into the application. In application, there is a load applied on the bolting joint. So as you can see here, the load applied on the joint will try to separate out the joint. So that is why you can see the load is always in the direction which is kind of a tensile direction on the bolt. So the applied load or the application load is in the same direction of the tension of the bolt, but it is opposite to the stack up clamping direction. So the clamping force that is applied here and the external load that is applied here, both you can see are in opposite direction. So it will try to relieve the joint from the clamping. So how it will happen? Once the external load applied reaches to the preload value, after that you start applying the external load further. That means I go on increasing the external load further. Till what extent I can apply an external load? so which should keep the stack up stable. So what you can see here, if you go on increasing the applied external load and you reach a point where the total deflection or the compression of the stack up is erased away, is totally relieved, that means the compression of the stack up is totally relieved. So at this point of time, the compression in the stack up is 0. So if you go on further increasing the load from here, what has happened is the joint is totally separated. So that is why this is called as the threshold or the maximum capacity of the bolted joint. So this, if I call it as PB max, so this is the maximum external load that can be applied on the given joint. So how do I know what is the value of this PB max? So henceforth it's only a simple geometry. What you can see here, it's a simple triangle, and to calculate the value of this PB max, I know the slope of this line and I know the total deflections. So the total deflection is delta B plus delta C, and the stiffness I know is KB in this case, stiffness of the bolt. So what I have done here is PB max is nothing but stiffness of the bolt into the total deflection. Total deflection here is deflection of the bolt plus deflection of the stack up. So delta C plus delta B. What we have seen from the deflection stiffness formula is that deflection is nothing but load divided by stiffness. So I have just replaced these terms, deflection by stiffness and preload. So if I take out the preload value out, what I see here is the value inside is KB divided by KC plus KB by KB. KB by KB turns out to be 1. So when I simplify this further, KB by KC plus 1 is actually KB by KC plus divided by KB. So this is the final formula that we have arrived at, is the maximum external load capacity is nothing but the preload into this particular factor. This factor is nothing but stiffness of the bolt plus stiffness of the stack up divided by stiffness of the bolt. Now one interesting thing to understand over here is that how do I know that if I have two, if I have one stack up and one bolt, if the bolt stiffness is higher than the stack up, what will happen? Or if suppose both bolt and stack up are having same stiffness, then what will happen? Or if suppose vice versa, the stiffness of the stack up is higher, what will happen? So let us just try to further evaluate this equation. What you can see here is that the total maximum for this particular maximum load, this factor, what could be the value of this particular factor? For theoretically speaking, okay. So from this equation, what you see here is the maximum capacity of the bolt joint is directly proportional to the preload into this particular factor. So this factor is very important, and it is based on only the stiffness of the stack up and bolt, the relation of the two parts. So what I have just tried to analyze this equation further. Let us assume that KB is 1 and KC is also is equal to 1. That means the bolt and stack up are having same stiffness. So in this case, what happens is, if I see here KB is equal to KC, in that case this particular whole bracket value will be equal to 2. So the PB max will be PI into 2, means the maximum load capacity of the joint is twice the preload value. Now what happens if KB is lesser than PB? So KB is say greater than KC. So if the bolt stiffness is higher than the stack up stiffness, then this particular factor comes out to be 1.5. If suppose the stack up is stiffer than the bolt, stack up stiffness is say twice the stiffness of the bolt, in this case that factor comes to be 3. So what we have seen here, if the stiffness of the stack up is higher, the load carrying capacity of the joint is higher. If the stiffness of the bolt is higher, like in this case, if the stiffness of the bolt is higher, the stack up capacity is lesser, 1.5. What I have technically tried to again do is I tried to plot this same equation on using a computer, and what I found is if you just plot KB versus KC on the 45-degree line, what you have seen is KB is equal to KC. In that case, this particular factor is equal to 2, correct? If the KB, if the bolt stiffness is higher, in this case, this value goes on. You will have further lines like this, and if the KB is greater than KC, the value goes on reducing. So from 2 it will again become 1.5, then 1.2, and subsequently further. And if this KC, the stack-up stiffness, is higher than KB, in this case what will happen is we will have further lines like this, where the stiffness, this particular factor value will go on increasing, like say 2.5, 3, 3.5 and further. So the conclusion to make here is, if you want to have a stable joint where you want to have a higher capacity of the bolted joint, in that case it is always preferred to have a stiffer stack-up and a softer bolt. That means, for example, if I have two plates of say aluminium which are clamped by a steel bolt, so in that case what will happen, the stiffness of the stack-up is lesser and the stiffness of the bolt is higher. So in this case the chances of bolt loosening is higher. If the stiffness of the bolt stack-up is high, in that case the chances of bolt loosening are less.